Welcome to the generational rewrite, a systemic mapping of the frontier infrastructure stack. What you're looking at on screen is not just a diagram, it's a map of civilization scale transition that is happening right now, hidden inside the data centers, semiconductor fabs, and energy grids around the world. For decades, we built computing systems around a simple idea: faster processors, more memory, better software. That paradigm has run its course. The architectures that provided the internet revolution cannot power the intelligence revolution. They are not merely insufficient, they are architecturally incompatible. What we are witnessing today is a generational rewrite, not an upgrade, not an iteration, a complete teardown and rebuild of the entire stack. From the electrons moving through silicon all the way up to the products that sit in people's hands. This presentation synthesizes insights from global leaders who are actively solving the fundamental bottlenecks in the compute, models, and deployment. We will move through each layer of the stack: the physics constraints, the silicon realities, the intelligence modalities, and capital dynamics to give you a complete map of where we are, what is broken, and what the new world looks like when it's built. By the end, you won't just understand frontier AI, you will understand the infrastructure substrate that makes the frontier AI possible, and why solving each bottleneck sequentially unlocks the next. Let's begin. The infrastructure stack is undergoing a fundamental rebuild. The first thing to understand is the scope of what is being rebuilt. On the left of your screen is the legacy stack. It's elegant in its simplicity. Physical infrastructure at the base: servers, cooling, networking. Application servers sit on the top. Sequential processing handles requests one at a time. Data is stored in SQL or NoSQL databases. Load interfaces distribute traffic. And at the top, end users consuming application over the internet. This architecture powered every major technology company for the past 30 years. It is highly mature, deeply optimized, and globally deployed. It is also completely wrong for what comes next. On the right is the frontier stack, and the contrast is stark. At the base, instead of commodity physical infrastructure, you have frontier energy generation, nuclear reactors, dedicated renewable installations, because what comes above them requires power at a scale the commercial grid was never designed to deliver. Above that, instead of application servers, you have parallel computing arrays, GPU and TPU clusters operating in tight coordination, running billions of operations simultaneously. Instead of sequential processing, you have massive parallel compute that is elastic and scalable. The data center itself becomes a single distributed computer. And at the top, instead of deterministic software applications, you have generative models and dynamic neural meshes, systems that learn, adapt, and produce outputs that no human explicitly programmed. The transition between these two worlds is not a migration, it's a rewrite. Every assumption about how systems are built, powered, cooled, and deployed must be reconsidered from first principles. The companies and nations that complete this rewrite first will define the intelligence era. Navigating the frontier architecture. To navigate this complex rebuild, it helps to think in layers. The frontier architecture has three distinct layers, each governed by different rules, different constraints, and different decision makers. Layer 1 is the base layer. This is the physical realm of electrons and silicon. It is governed by absolute resource constraints, by physics. How many transistors can you fit on a chip? How many watts can a data center absorb? How fast can heat be removed from a processor? These are not engineering preferences. They are physical laws. Decisions made at layer 1 cascade upward and determine what is possible everywhere above. Layer 2 is the intelligence layer. This is the algorithmic realm, the world of unified models, visual systems, and voice interfaces. It is governed by modality parameters, the specific mathematical architectures that transform raw compute into useful intelligence. A vision model is fundamentally different from a language model, which is fundamentally different from a spatial reasoning system. Each requires different data, different training regimes, and different inference infrastructure. Layer 3 is the ecosystem layer. This is the deployment realm, the world of product management, venture capital, and network effects. It is governed by human intent. What do people actually want? What products create compounding adoption? Which go to market strategies unlock distribution? Layer 3 is where raw intelligence meets the market, the critical insight. And we will return to this at the end, is that these layers are not independent, they're interdependent in both directions. A breakthrough at layer 1 unlocks new capabilities at layer 2. New capabilities at layer 2 create new product categories at layer 3. Revenue from layer 3 finances the next round of layer 1 infrastructure. This is the flywheel. Understanding is everything. Theoretical demand collides with physical reality. Two hard physics constraints throttle AI at scale, energy grid capacity, and silicon manufacturing yields. Here's the central tension of the frontier era, rendered visually. At the top of this diagram, you'll see full breadth of theoretical global AI demand. Every researcher who wants to train a model, every company that wants to deploy intelligence, every government racing to build sovereign AI capability, every startup that has identified a billion-dollar use case that requires compute to exist. That demand is enormous. It is distributed, it's urgent, and it's growing faster than any infrastructure build out in history. Now look at what happens as that demand flows downward. It narrows dramatically because theoretical demand must pass through the physics constraint, a bottleneck so fundamental that no amount of funding or urgency can dissolve it overnight. On the left of the bottleneck, the label reads energy grid limitations. The sheer megawatt capacity required to spin up and sustain training clusters. You cannot wish away the law of thermodynamics. You cannot fund your way past the grid interconnection queue. Training a frontier model requires concentrating energy at a density that the existing electrical infrastructure was not designed to support. On the right, silicon yields, the manufacturing reality of producing advanced parallel compute architectures at scale. Every leading edge GPU, every TPU, every next generation AI accelerator must be physically fabricated. That process involves atomic level precision manufacturing with inherent yield limitations. The world has exactly 3 or 4 facilities capable of producing these chips at the frontier. The output is finite. Between those two constraints, the energy and the silicon, the pipe narrows. And the delta between what the world demands and what physics can deliver is the defining tension of this era. Everything that follows in this presentation is about navigating, engineering around, and ultimately expanding that bottleneck. Intelligence is ultimately bound by megawatts. Let's go deeper on the energy constraint because it's the most underappreciated bottleneck in mainstream disclosure about AI. When most people think about AI scaling, they think about chips and software. But the binding constraint right now, the thing that actively throttling the pace of intelligence development, is power. The current power grid infrastructure was not designed for concentrated, sustained draw required by the frontier training runs. When a hyperscaler builds a traditional data center, they might draw 50 to 100 megawatts from the grid. Substantial but manageable. A frontier training cluster for a leading edge model needs 200, 300, sometimes 500 megawatts continuously. For weeks or months, that is not a data center. That is an industrial facility. It is closer in power drawn to an aluminum smelter than to a server farm. Look at the pressure gauge on the slide. The needle is sitting in the red zone, not at peak load, but at the threshold labeled critical overload. Frontier training runs. The traditional base load supply line sits far below where the frontier workloads require. The grid cannot be flipped on like a switch. The grid interconnection takes years. Permitting takes years. Construction takes years. The topographic map shows you the geographic reality. Gigawatt scale data center clusters, shown as the highlighted zones, are interconnected by ultra high power transmission paths. But the legacy grid shown in gray is insufficient for this topology. The clusters need direct, dedicated energy feeds that the grid was never designed to provide. This is why you're seeing frontier AI companies partner directly with nuclear operators, sign long-term renewable power purchase agreements, and in some cases pursue direct co-location with power generation facilities. Energy has become the primary bottleneck for scaling intelligence. Full stop. Until this is solved, everything else is secondary. Silicon architecture determines capability bounds. Assuming you can deliver power at scale, the next question is, what do you do with it? The answer requires understanding why traditional CPU architecture is fundamentally incompatible with frontier AI workloads. Look at the diagram on the left. This is a traditional CPU. It has a single large, extraordinarily powerful processing core. Information enters, moves through a serial processing pathway, and exits as output. For decades, this was the right architecture. Most software tasks, fetching a web page, executing a database query, running a business logic function, are inherently sequential. One thing has to happen before the next thing can happen. But notice what happens at the entry point of the CPU when the workload intensifies. You see it, the orange heat signature, congestion, a bottleneck. The serial pathway can only move information so fast. You can make the core faster, but there is a physical ceiling. Clock speeds stalled a decade ago. Dennard scaling is dead. Now look at the right side of the diagram. This is the frontier GPU architecture. Instead of one large core, you have thousands of smaller cores. The energy inflow is not a trickle. It is a massive concurrent flood entering from multiple directions simultaneously. And inside the chip, all of these cores are working in parallel, simultaneously processing thousands of matrix multiplications, vector operations, and attention computations. This architecture exists because intelligence computation is embarrassingly parallel. When you run a transformer model, nothing depends on completing one token before you compute the next layer. The whole operation can be parallelized across thousands of cores. Grid energy flows in, mathematical probability flows out. The process in frontier AI requires redesigning the entire data center as a computer, not a warehouse of individual machines, but a single tightly coupled parallel compute fabric. That is the architectural shift that silicon must enable. Compute distills into distinct intelligence modalities. Once you have solved the energy problem and built the parallel compute fabric, you face the next challenge. Raw computational power has no intrinsic form. It must be shaped, distilled into specific modalities that humans can actually interact with. Think of the diagram on this slide as a prism. Raw compute and infrastructure enters from the left as a single beam. It passes through the intelligence layer, through training architectures, modality parameters, modal separation constraints, and it refracts into three distinct outputs. The first output is the voice systems. This is the modality that handles natural language processing, acoustic modeling, and signal processing. The core challenge of voice is not transcription. Speech to text has been solved for years. The frontier challenge is real-time, emotive compute, generating speech that doesn't just convey words, but conveys meaning, emotion, cadence, and naturalness at a latency that feels instantaneous to a human listener. The second output is visual intelligence. This covers computer vision, image generation, and object recognition. The computational signature of visual intelligence is burst heavy. Generating a high resolution image requires enormous compute concentrated in a short window. As the model iteratively refines millions of pixel values from noise to coherent output. The third output and the most compute intensive is unified 3D systems. This is spatial computing, simultaneous localization and mapping, physics simulation, object permanence modeling. Unified intelligence must understand the physical world, not just the pixel world. Each modality has a distinct compute profile, a distinct data requirement, and a distinct set of ecosystem bottlenecks. The refractive index of the prism, the model specificity, determines exactly how raw compute translates into each output. Understanding these distinctions is not academic. It determines which infrastructure investments you make, which companies you back, and where the next capability breakthrough will emerge. Synthesizing reality through visual intelligence. Visual models require immense compute to perform diffusion, iteratively resolving high complex, high resolution pixel data from structural noise based on semantic understanding. Let's examine the visual intelligence modality in detail because it illustrates something profound about how modern AI systems work and why they require the infrastructure we have been describing. The process is called diffusion, and it is one of the most counterintuitive breakthroughs in the history of machine learning. Look at the left panel: complete entropy, pure noise, statistically random pixel values with no structure, no meaning, no information. This is where the process begins. Now, look at the right panel: a high fidelity architecture rendering, coherent structure, precise geometry, accurate lighting, rich detail. This is where the process ends. What happens in between is the magic and the reason it requires immense compute. The model does not draw the image. It does not fill in pixels from a template instead. It iteratively reduces the noise. At each step, it asks, given everything I know about what this image should contain, given the semantic text input, given the patterns learned from billions of training images, which direction should I nudge each pixel to make this less noisy and more coherent? This question is asked thousands of times. Each iteration requires running the full neural network forward pass, billions of matrix multiplications across millions of pixel locations, across hundreds of time steps. The middle panel shows an intermediate stage. You can see structure emerging from noise, but it's still rough, still uncertain, still resolving. The computational requirement is staggering. A single high-resolution image generation might require as much compute as serving thousands of traditional web requests. And the resolution scaling is brutal. Doubling the image dimensions quadruples the compute requirement. This is the compute signature of visual intelligence. Heavy burst generation, followed by silence, followed by the next burst. Now let's explore voice systems. Voice systems require absolute latency eradication. The frontier of voice systems is not just text-to-speech, but real-time emotive compute. The challenge is compressing generation times so tight that the machine response feels instantaneous and biologically natural. Voice is the modality where the physics of computation meets the biology of human perception most directly, and the constraint is unforgiving. Look at the waveform on this slide. This represents natural human speech: dynamic, emotive, tonally varied, syntactically complex. Notice the annotations: dynamic, emotive, human speech, tone variation, syntactic complexity. This is not flat text. This is a rich, multidimensional signal that carries meaning, not just in words, but in the pauses, the inflections, the rhythm. Now look at the orange box at the bottom left of the timeline. The box marks the biologically natural latency threshold, 0 to approximately 200 milliseconds. 200 milliseconds is not an engineering preference. It is a human neurological reality. When a response arrives within 200 milliseconds of a conversational input, the human brain experiences it as immediate, natural, flowing, and conversational. When the response arrives at 300 milliseconds, 400 milliseconds, or beyond, the brain registers a gap. The illusion of natural conversation breaks. The experience degrades from talking to an intelligent entity to waiting for a machine. Now look at what has to happen inside the orange box. The system must receive audio input and decode it, run it through the language model, generate a response, convert that response into speech, apply emotional prosody, render the acoustic waveform, and deliver it. All of that, every single computational step, must complete in under 200 milliseconds. This is why voice systems require a fundamentally different infrastructure than visual systems. There's no tolerance for burst latency. There's no user who will accept buffering. The pipeline must be so tightly optimized, so deeply hardware accelerated, that the entire chain from input to output completes in a time window narrower than a human eye blink. Absolute latency eradication, not reduction, eradication. Now let's go to the third modality. Unified intelligence demands spatial and physical grounding. True unified intelligence transcends 2D pixels or audio. It requires the model to understand the physics of the world, object permanence, lighting, depth, and spatial relationships, creating highly compute intensive 3D simulations, like for example in the case of a self-driving car. The third modality, unified intelligence, is most ambitious and most compute intensive. And to understand why, you need to think about what it actually means for an AI system to understand the physical world. A language model understands text. A visual model understands pixels. But the physical world is neither text nor pixels. It is a continuous, three-dimensional, dynamically evolving environment governed by physics. Look at the diagram on this slide. You see a drone suspended in a coordinate space defined by three axes, x, y, and z. Around it, the annotations tell the story of what unified intelligence must compute in real time. Velocity vectors. Where is the object going and how fast? Collision boundaries. What objects are nearby and will they intersect? Physics calculations. What are the friction coefficients, the contact forces, the effects of gravity? Depth perception algorithms. How far away are objects in the scene? Spatial data flow. How is the environment changing moment to moment? Each of these computations is demanding in isolation, together, running simultaneously, running in real time, running for every object in a complex scene. The compute requirements are extreme. Not heavy burst generation like visual intelligence, not ultra low latency like voice systems. Extreme continuous processing. Sustained uninterrupted across every frame, every millisecond, indefinitely. This is why robotics, autonomous vehicles, and spatial computing represent the frontier of the frontier. They require not just intelligence, but intelligence that is grounded in physical reality, systems that understand that objects fall when dropped, that surfaces have friction, that two objects cannot occupy the same space. The current ecosystem bottleneck for this modality is physics engine accuracy, the gap between approximate simulation and true physical fidelity. Closing that gap is one of the defining engineering challenges of the next decade. The intelligence modality matrix. Let's consolidate the three intelligence modalities into a single comparative framework, the intelligence modality matrix. The three columns represent the current generation of frontier companies pushing each modality to its limits. Unified systems, represented by companies like Luma AI, take spatial and three-dimensional geometry as primary data input. The compute intensity profile is extreme and continuous. There's no rest, no pause, no burst and wait cycle. The physics engine must run perpetually. And the current ecosystem bottleneck is physics engine accuracy. The challenge of simulating reality faithfully enough that models trained in simulation transfer reliably to physical world. Visual intelligence, represented by labs like Black Forest Labs, takes semantic text and visual noise as primary inputs. The compute profile is heavy burst generation, massive compute concentrated in short windows for each generation task. The current bottleneck is high resolution scaling. As users demand larger, higher fidelity, longer duration outputs, the compute requirements scale faster than the infrastructure currently supports. Voice systems, represented by companies like 11 Labs, work with text and audio waveforms. The compute profile is ultra low latency optimization. The entire engineering challenge is about compressing the pipeline to fit within the biological tolerance window. And the current bottleneck is emotive edge cases fidelity, the gap between competent speech synthesis and truly natural, emotionally nuanced, contextually appropriate voice generation. Now look at the highlighted row. Current ecosystem bottlenecks. Physics engine accuracy, high resolution scaling, emotive edge case fidelity. These are not abstract research problems. They are specific, tractable engineering challenges where capital investment will unlock the next wave of capability. Understanding where each modality is bottlenecked tells you exactly where to build and what to build. Models must be packaged for human deployment. Raw intelligence holds zero economic value until directed. Product architecture and capital deployment package models for market. Here's the truth that gets lost in the excitement about frontier models. Raw intelligence holds zero economic value until it's directed. A trained neural network sitting on a GPU cluster with no product wrapper, no deployment infrastructure, no user interface, no distribution is worth nothing. It is a scientific artifact. It's a capability without a delivery mechanism. Look at the left column of this diagram. This is what a model actually looks like internally. Unstructured networks, a vast tangled web of weighted connections, raw algorithmic power, mathematical structure without shape or purpose. This is what billions of dollars of compute and months of training produces. Now look at the right column. This is what a market-ready product looks like. Useful apps, scalable systems, structured outputs, products that a human can open on their phone, interact with, pay for, and return to tomorrow. The gap between those two things, between a raw model and the market product, is the middle column, deployment protocols. Product architecture is the first deployment protocol. Someone must decide what the model does, what it doesn't do, how it handles edge cases, how it presents itself to users. These are not trivial decisions. The product architecture transforms a probabilistic system into a reliable experience. Capital deployment is the second protocol. Infrastructure does not build itself. The servers, the APIs, the CDN distribution, the redundancy, all of it requires continuous investment. Validation gates are the third. Before a model ships, it must be tested, red teamed, evaluated against safety benchmarks, monitored for harmful outputs. The validation layer is what makes commercial deployment responsible. The pipe runs left to right, raw intelligence through deployment protocols into the markets. Every company that successfully completes this pipeline owns the value chain from physics to product. Navigating probabilistic outputs in product architecture. Product management in AI era requires a fundamental pivot. PMs no longer manage deterministic code loops. They must design systems that gracefully handle variance, user intent ambiguity, and non-deterministic behaviors. One of the most profound shifts of the intelligence era is one that most people outside the industry haven't fully grappled with. The nature of software itself has changed. Look at the left side of this diagram. This is traditional software. A user clicks a button, fixed code executes, and exact expected result is returned. The same input always produces the same output, always. This is the foundation of software engineering as it has been practiced for many years. It is deterministic, reproducible, testable, debuggable. Now look at the right side. This is an AI era system. A user inputs something, but that input is fuzzy. It's not a click, not a precise defined API call. It's a natural language intent that might be ambiguous, incomplete, or contradictory. The model generates a probabilistic output, not a fixed answer, but a distribution of possible answers shaped by the parameters of the model, the context of the conversation, and the stochastic elements of sampling. The output of a frontier model is never guaranteed. The same prompt run twice produces different results. This is not a bug, this is a fundamental property of the architecture. For product managers, this requires a complete pivot. You can no longer design products around deterministic guarantees. You must design systems that gracefully handle variance, systems that can catch bad output before they reach users, systems that interpret ambiguous intent rather than rejecting malformed input, systems that improve over time through feedback, not through explicit reprogramming. The product wrapper, shown in orange on the right side, is what bridges the gap between probabilistic model output and the formatted user value. It catches, it refines, it adds guardrails, it structures the chaos into something reliable. This is why product management in the AI era is harder, not easier, than it was before. The craft has moved from managed code to managing probability. Capital deployment ignites the infrastructure flywheel. Because the base layers of compute and energy are extremely capital intensive, venture networks act as the initial catalyst. The resulting product network effects secure the financial viability of the entire stack. We have mapped the physics of the stack, we have mapped the intelligence modalities, we have mapped the product layer. Now let's talk about the force that sets all of it in motion: capital. Because the base layers of compute and energy are extremely capital intensive, we are talking about billions of dollars to build a single frontier training cluster, tens of billions to build out gigawatt scale energy infrastructure. The commercial market alone cannot self-fund the build out. Venture networks act as the initial catalyst. Look at the flywheel. Stage 1, venture capital injection. Risk capital flows in at the top of the cycle, providing the fuel to begin. This capital does not produce immediate returns. It is buying optionality on a future where the infrastructure stack is complete. Stage 2, the physical infrastructure. Scaling. The capital flows into electrons and the silicon, energy infrastructure, GPU, procurement, data center construction, networking fabric. This is slow, physical, capital intensive, and irreversible. Stage 3, unlocking model capabilities. With infrastructure in place, training runs can proceed, and each increment of scale unlocks nonlinear improvement in model capability. This is the phenomenon known as emergent capabilities, abilities that appear suddenly as scale crosses certain thresholds. Stage 4, generating user network effects. Capable models attract users. Users generate data. Data improves models. More capable models attract more users. The network effect compounds. Stage 5, capturing financial returns. Revenue flows back into the system. Profitable products fund the next round of infrastructure investment. The flywheel accelerates. This is not theory, it is the observed dynamic of every major frontier AI company today. The cycle is real. The question is which companies complete it and which stall at which stage. Capital is not merely one input among many, it is the ignition system. The frontier system architecture, the generational rewrite is entirely interdependent. Breakthroughs in software are gated by infrastructure. Infrastructure is gated by capital. Capital is validated by product adoption. To solve one bottleneck is to unlock the next. We end where we begin, but now we can see the whole picture. The frontier systems architecture, at the bottom left, you see energy generation, power towers, nuclear facilities, direct feeds. This is the foundation. Without electrons, nothing above it exists. From energy, power flows into parallel processing architectures, GPU and TPU arrays, each consuming hundreds of megawatts, transforming electrical energy into mathematical computation. That computation feeds three intelligence systems: visual intelligence on the left, the processing and generating images and video, voice system in the center, listening and speaking in real time, unified intelligence on the right, reasoning about the physical world in 3 dimensions. All three converge into the product management layer at the top, the human facing interface where raw capability becomes useful experience, where user research meets feature definition, where market validation meets product iteration. And wrapping the entire system, the orange loop you see circling everything is the capital flow loop. Investment flows in, adoption validates, returns reinvested. The system scales. But here's the most important insight of the entire presentation. The generational rewrite is entirely interdependent. Breakthroughs in software are gated by infrastructure. You cannot build a better model if you don't have the compute to train it. Infrastructure is gated by capital. You cannot build the compute if you don't have the investment. Capital is validated by product adoption. You cannot sustain investment if you don't have the products that people use and pay for. To solve one bottleneck is to unlock the next. There's no shortcut. There's no way to skip a layer. This is why the companies and the nations that take a system level view, who understand that energy, silicon, models, products, and capital are not separate problems, but a single interdependent stack, are the ones who will define the intelligence era. The generational rewrite is underway. The question is not whether it will happen. The question is who builds it. Thank you.